this is a video on stoichiometry. Now, in this video, I'm going to go over, obviously, the definition of stoichiometry, but I'm also going to go over the different types of problems you're going to see in a stoichiometric situation. Okay, so stoichiometry is a branch of chemistry that deals with the relative quantities of a species in a balanced chemical reaction. Now, when I'm referring to species, I'm talking about the reactants and products within an equation. Okay, so for an example, ammonia production is from hydrogen gas and nitrogen gas. So I have the equation written right there. Now, the numbers, we always been talking about individual, atoms that we're looking at, right? We have, 6 hydrogens and 2 nitrogen atoms on one side, and of course we should have 6 hydrogens and 2 nitrogen atoms on the product side. Okay, so they need to be equal. So when I look at, say, another slide, and I have a different meaning for those coefficients now, okay, it's going to be important for your ability to solve problems, okay, because they do mean molecules, right? Or in this case, they could mean formula units such as molecules or atoms, okay? But they also mean moles, okay? It's not just 3 molecules of hydrogen gas and 1 molecule of nitrogen gas react to form 2 molecules of ammonia gas. Okay, it also means that 3 moles of hydrogen gas, right? So 3 times 6.02 times 10 to the 23rd molecules of that gas, right? 3 moles of hydrogen gas and 1 mole of nitrogen gas will form 2 moles of ammonia gas. Okay, it's important to note that because these mean moles, we can actually derive a molar ratio. And that molar ratio will be able to have us go from, say, one substance, say nitrogen, to another substance, ammonia. And you're thinking, well, what do you mean by going from one to another? The type of question that you're going to come across with stoichiometry is the application of dimensional analysis to equations, right? If I have X amount of hydrogen gas, how much hydrogen gas can I, or how much ammonia gas can I form based on the amount of hydrogen gas that I started with, okay? Now, when you're looking at this, we should first be able to identify how to get a molar ratio, right? Well, a molar ratio is going to be the numerical relationship between 2 species in a chemical reaction. So I'm looking at this same equation, okay? 3 moles of hydrogen, 1 mole of nitrogen makes 2 moles of ammonia, right? There's a lot of different relationships here, right? I can have, oops, that's not what I want. Okay, okay, sorry. So I have a lot of different relationships right here, right? I have 3 different species, and I'm going to have relationships for each one of them with at least one other one. And what I mean by that is, for example, I'm going to have a hydrogen to nitrogen ratio. I'm going to have a hydrogen to ammonia ratio, and I'm also going to have a nitrogen to ammonia ratio. Okay? And the ratio that I'm referring to, that numerical relationship, is just the coefficients that are present in the balanced chemical equation. So what I mean by that is the molar ratio of hydrogen gas to nitrogen gas is 3 to 1. Or from nitrogen gas to ammonia gas is 1 to 2. Or from hydrogen gas to ammonia is 3 to 2. Okay? Now I can use those types of problems, or use those types of ratios to predict how much of one species I can either use up if I'm a reactant or make if it's a product. Okay? Okay, so if you look here, I have a little diagram so you guys can see. I'm always going to have a known and an unknown, or a given and an unknown, just like dimensional analysis problems. But now my dimensional analysis is going to revolve not so much in a sentence as much as an equation, right? I'm going to have a chemical equation, and then the chemical equation is going to give me the given, and it's going to give me the unknown through the molar ratio to begin with, right? So, like for example, if I had the moles of 1, I can use molar ratio, okay, to get moles of the unknown, or moles of what I want. Now, what a problem like that would look like okay, is if I was to have our same balanced chemical equation, and let's say I started off with, 2.6 moles of nitrogen gas, right? I want to know how many moles of ammonia can be made if I start with 2.6 moles of nitrogen gas, right? Now, I'm going to have a lot more examples, okay? In fact, I have an entire video just on molar ratio, which is going to be our first step. So, but I'll still do one right here, right? I'm going to start with what I'm given, just like all the other dimensional analysis problems, right? 2.61 moles over nitrogen over 1, okay? And here is where I'm going to use my molar ratio, right here, okay? I know I need moles of nitrogen on top, or on bottom, excuse me, and I need to get moles of ammonia, right? Should be moles of ammonia. That's what I want. So I'll put moles of ammonia on top, okay? So what is my molar ratio of nitrogen to hydrogen? Well, nitrogen is 1, or nitrogen is 1 and ammonia is 2. So I have 1 mole of nitrogen for every 2 moles of ammonia. Okay, my moles of ammonia my moles of nitrogen cancel out. I'm left with moles of ammonia. Okay, so that would be 2.6 times 2, which would be 5.2. Okay, make sure we're maintaining our sig figs. And it's important to know that molar ratio is not going to play a part in sig figs. Okay, usually if you just stick with the number that you're starting with, the number of sig figs, in this case I have 2 sig figs right there, my answer should have 2 as well. Okay, so I have 5.2 moles of ammonia, run a room, over 1, right, because my units of moles nitrogen canceled out. So my final answer is 5.2 moles of ammonia. Okay, now there could be times I'll ask you to give me a complete sentence and say, 2.6 moles of nitrogen gas will produce 5.2 moles of ammonia. Okay, but this is how you do it. Molar ratio problems are really easy. They're one-step dimensional analysis. Okay, now some of the other problems that we're going to have, and in fact the majority of the problems we're going to have, are going to deal with mass, right? The reason why mass is because it's something that we can measure in a lab. We can go to a balance and we can get mass. I can find out how many moles of water if I have the mass of that water, right? And the reason why we have this relationship between mass and moles is because we have the periodic table, and that periodic table gives us a molar mass. Okay? So, if you look, this is just like this box right here, this arrow right here, is just like our previous diagram, right? This will be molar ratio, and then molar mass is going from moles to grams. Okay. Now, could I go from moles to formula units, such as moles to atoms, or moles to molecules, or moles to ions? Sure, I could, but we're not really going to focus on going to formula units and using Avogadro's number. That's not going to be a big part of this unit. The big part of this unit is going to be the uses of molar ratio and the uses of molar mass. Okay? So if you know how to get the molar ratio and you know how to get the molar mass and you know how to use them in dimensional analysis, then this unit's going to be cake for you. So now let's look back at that similar problem that we had, right? We had 2.6 moles of nitrogen gas, but now instead of saying I want a number of moles of ammonia, what if I want the mass of ammonia, and usually it's in grams, right? I want the mass of ammonia now, right? Thing is, I had 2 arrows on this diagram, right? Right? We had 2 arrows. We had this arrow right here, and we had this arrow right here. Okay, each arrow is representing a step of dimensional analysis. So for this problem of going from moles of nitrogen to grams of ammonia, I'm going to have a 2-step dimensional analysis problem. Okay, so 2.6 moles of nitrogen is going to produce how many grams of ammonia? That's what I want to find out. Okay, so I'll start with what I'm given, which is 2.6 moles of nitrogen. Put it over 1. Okay, and then I need to use a molar ratio here because I got to get to moles of ammonia before I can get to grams of ammonia. Moles is going to be your bridge. So I look at my molar ratio and I see that I have 1 mole of nitrogen gas for every 2 moles of uh, ammonia. Okay? Now I'm not where I want to be. I want to be at mass, but all I'm right now, I'm at moles. So I need to use molar mass, right? And just to refresh your memory, right? Nitrogen is 14.01, and then there's only one of them, but I need 3 hydrogens, which is equal to 3.03. So my molar mass for ammonia is going to be 17.04, right? Well, 1 mole of ammonia, because I need it on bottom, is 17.04 grams of ammonia. Okay, my moles of ammonia cancel out, my moles of nitrogen cancel out, and I am left with what, 2.6 times 2 times 17.04 grams of ammonia, all over 1 times 1 times 1. Okay, my final answer being, remember, with only 2 sig figs, will end up being 89 grams of ammonia. Okay, so if I was to ask you for a sentence of this, it would be 2.6 moles of nitrogen gas will produce 89 grams of ammonia. Okay, so let's look at a couple different types here. Okay, the next type of problem is going from given a mass and then getting to moles. Okay, well, if I'm going from mass to moles, I need to use molar mass. If I'm going from moles to moles, I'm going to use molar ratio. All right, so let's go ahead and take a look at a problem. Okay, obviously keep things simple, we're going to keep using the same equation, but let's go ahead and change it up a little bit. I want to say I'm starting with 62.45 grams of hydrogen gas, and I want to know how many moles of nitrogen gas will react with that much mass of hydrogen. Okay, so again, this is a two-step dimensional analysis. So I'm going to start with what I'm given, which is 62.45 grams of hydrogen, right, over 1. And then I need to get to moles, so I can get to a molar mass. Or not molar mass, but get to a molar ratio. So I'll use molar mass of hydrogen. In this case, the molar mass of hydrogen is going to be 2.02 grams of hydrogen, since it's diatomic, right? And this is for every 1 mole of hydrogen. And then for every, now here's the trick, there's 3 moles of hydrogen here, and there's 1 mole of nitrogen there, so you got to use a molar ratio. There's 3 moles of hydrogen for every 1 mole of nitrogen. Once I've gotten to that point, then I have what I want, right? So my moles will cancel out of hydrogen, my grams of hydrogen will cancel out, and I'm left with the number of moles of nitrogen. Okay, so I'll end up getting 62.45 times 1 times 1 mole of N2 all over 1 times 2.02 times 3. Okay, now if we recall, right, I don't have just ones on my denominator side. I have to apply sig figs to both top and bottom. Remember, since the molar ratio does not apply to sig figs, I'm going to have 3 sig figs here, and I'm going to have 4 sig figs there. So I'm going to have 62.45 divided by, what would that be, 6.06, leaving my final answer with 3 sig figs being 10.3 moles of nitrogen. Okay. Again, if I ask for a sentence, 62.45 grams of hydrogen will react completely with 10.3 moles of nitrogen. Okay. So the next one is the big one. Okay, this is the one where you're going to see a majority of your problems are going to be like this. Okay, so here you go. I'm given a mass, and I need to find a mass. So I have mass to moles, right? So I'm going to have 1, 2, 3 steps for dimensional analysis. So I'm going to have a 3-step dimensional analysis problem, as most of them are for your worksheets. Okay, here I got to use molar mass. Here I use molar ratio, and here I use molar mass again because I'm going from mass to moles. Okay, going mass to moles or moles to mass, I need to use molar mass. Right? That's why I'm using molar mass twice. But the difference is here I'm going to use the molar mass of my given, and here I'm going to use the molar mass of my unknown. And then use the molar ratio here to go from moles of what I have to moles of what I want. Okay? So let's take a look at an example problem. Like I said, I'm going to have a lot more example problems on another video for this type of problem. So you're going to have a video for your molar ratio problems, and then you're also going to have one for this type of problem, which is a true stoichiometry problem. Okay, so again, same equation, right? 3 moles of hydrogen gas react with 1 mole of nitrogen to form 2 moles of ammonia. Okay, so in looking at this equation, let's say I had 16.23 grams of hydrogen gas, and I want to know if I have enough nitrogen, because we'll talk about the relationship or the amounts of each reactant later, but let's say I had more than enough nitrogen to react with the 16.23 grams of hydrogen. I want to know how many grams of ammonia I can make. Okay? So if I know how many grams of ammonia I can make, then I can use that in whatever laboratory experiment I need. Okay? And it all revolves around the ability for you to write out an equation, balance it, determine the molar ratio, and calculate molar mass and use it. Okay? And we're going to use all of that right now. Okay? So, again, start with what I'm given. 16.23 grams of hydrogen gas over 1. And I need to get to moles of hydrogen. So 2.02 grams of hydrogen gas is for every 1 mole of hydrogen gas. And I use molar ratio right here, right? My molar ratio in this case is going to be 3 moles, according to the equation, right? 3 moles of hydrogen gas to 2 moles of ammonia. Okay, this is why it's so important to have your species written in the dimensional analysis like I've been telling you guys to do. Because if you don't have these units in here, then a lot of these units look the same. They're all grams and moles. You don't know which one's going to cancel out. You don't know which one you shouldn't cancel out. Okay? So continuing on, one more step is going to be 1 mole of nitrogen or ammonia is going to be 17.04 grams of ammonia. That's ammonium. Ammonia is with a 3. Okay? So set my problem up. Oh, sorry, excuse me. Cancel my hydrogens. I cancel my moles of hydrogen. I cancel my moles of ammonia. I'm left with my moles, or grams, excuse me, of ammonia gas. So 16.23 times 1 times 2 times 17.04 grams of ammonia. And that, oh sorry, excuse me, divided by 1 times 2.02 times 3 times 1. Okay, again, let's make sure we can identify our number of sig figs, right? I have 4 here, I have 4 here, so my numerator is going to have only 4, because these two guys right here, this is the exact number, and that's a molar ratio. So I'm going to have 4 sig figs here, and then down on the bottom, I have 3 sig figs here, so my final answer should have 3 sig figs. Okay, because the slide's so small, I'm going to delete everything. So make sure you have this written down. Okay. Okay, now that that's rewritten, okay, I'm going to go calculate real quick. 16.23 times 1 times 2 times 17.04. I'm going to end up with 4 sig figs, 3.1 divided by 6.06. What the heck happened there? 1. Okay, so 553.1 divided by 6.06 is going to equal 91 with 3 sig figs, right? 91.3, because I have 3 sig figs here. 91.3 grams of ammonia. So, question. If I had 16.23 grams, right, this is what I started with. If I had 16.23 grams of hydrogen gas, I could make, assuming I have enough nitrogen, 91.3 grams of ammonia. Okay? So, like I said, there's going to be a couple more videos. One's on molar ratio. The other one is going to be on some more stoichiometry problems just like this one. Okay? If you have any questions, by all means, shoot me an email or ask.